And lastly, we have sigma, where sigma is 1.5. All right. So just remember, anytime you have sigma, that means we're going to be using the Z distribution. Okay, in a little bit, we're going to be going over when to use the T distribution, and you use the T distribution if you don't know sigma. So very important that you just know you use the Z distribution if we are given sigma or the population standard deviation. If we're not given sigma or the population standard deviation, you want to use the T distribution. But we'll get more into that once we get to the T distribution. But any question for mu or sigma? Alrighty. So up next, we're going to go ahead and do, I'm going to go to the TI-84. And we're going to start entering the data into L1. So we'll say on, we'll go to stats, we'll go to edit. And in edit, well, we're going to edit it and enter this data set. So you do 10.7, 3.2, All right, so I enter all 33 data set. Now that I enter all 33 data set, I'm gonna go ahead and start running the test. So to run the test, we're gonna go right here where it says stats. You're gonna move it over 2 spaces where it says test. And we're gonna use the first one that's the Z test. So we'll say Z test. So if you look at it, since I entered data set into L1, you want to tell the calculator to look for that data set. So I'm going to move it over to data, press enter. For mu, we're going to enter 6 years. For sigma, it was 1.5 year. For list, since I entered my data set into L1, that's where I'm going to tell the calculator to look for it. If you enter it somewhere else, you want to tell it where to look for it. So if you put it in L2, tell the calculator to put in L2, but the calculator always have a default to L1, so it'll be smart for you. You have to always put the data set into L1, for that way the calculator automatically look there. Frequency will always be 1 in this case. And lastly, we want to put the alternate hypothesis. If you remember the alternate hypothesis, we said that it should be greater than. So you want to select the one that says greater than. And go there. All right. Any question on anything that inputted into the Z test? All right, so I'm gonna go ahead and just go calculate. So if you look at when I go calculate, it gives me a Z value. So I'm gonna go ahead and make note of that. So the Z value they give me is roughly 1.93. Also, if you look right here where it says P is 0.027. So I got myself my Z value and my P value. And for this one, will we call this a left tail test, right tail test, or will this be a two tail test? And to kind of decide if it should be a left tail, two tail, or a right tail, you do want to use the alternate hypothesis to decide if it should be a left tail test, a two tail test, or a right tail test.
Right test?
Yeah, good. Yeah, if you look at it, since it says greater than will be a right tail test. So this should be a right tail test. If it was a less than would have been a left tail test. If it says not equal to, then that would have been a two tail test. All right. So let's go ahead and switch back to the notes. All right. So if you see what I already wrote down, this is 1.93. I already wrote this as a right tail test. So I get a p-value of 0.027. So let's go ahead, let's go and make our interpretation. So for interpretation, we have a p-value, which is 0.027. We have an alpha, and alpha is 0.05. So which one is bigger? My p-value, which is 0.027, or my alpha, which is 0.05?
Alpha.
Yeah, so it should be alpha. So since it's alpha, I'm going to select this first one over here. All right, so anytime alpha is bigger than p-value, where you're going to say reject the null hypothesis. Any question in regard to that so far?
So because we use the calculator to figure out the z-score, we don't need to do some of those other steps up there, like the.
Yeah, no, we're going to skip that for now. All right. So once we reject the null hypothesis, that's when we want to do our conclusion about pretty much about the alternate hypothesis. So we want to say something about the alternate hypothesis. So we want to say, is there enough evidence to support the alternate hypothesis, or is there not enough information to support the alternate hypothesis? Right. So in this one, since we rejected the null hypothesis, so we're rejecting the null hypothesis that the mean is equal to 6 years. So we're kind of pretty much rejecting the fact that it takes 6 years or less than 6 years to quit smoking. So we're going to conclude the alternative, which the alternative was saying that it takes more than 6 years. So we're going to say there is enough evidence to support the claim that it takes All right, and that's it for that first problem of the day. So for this one, we'll say there is enough evidence to support the claim that it takes more than 6 years to quit smoking. And that's it. All right. Any question for that first problem?
Above earlier when, oh, excuse me. When you When we got the standard deviation of 1.5, you said we could use a z distribution. Does that just refer to the z-score we got on the calculator?
No, that doesn't refer to the z-score that we got from the calculator. They just refer to the z-score that they already knew.
Oh, okay.
So
Thank
they already knew that the population standard deviation was 1.5. So they already gave us that, but that 1.5 doesn't refer to the sample. Because if it would have been from the sample, like then that would have been a sample standard deviation.
you. Gotcha. Thank you.
You're welcome. All right, let's go on to problem 2. All right, so for this one says, suppose that an automobile manufacturer advertised that its new hybrid car had a mean gas mileage of 50 miles per gallon. You take a simple random sample of 30 hybrid vehicle and test their gas mileage. You find that in this sample, the average is 47 miles per gallon with a standard deviation of 5.5 miles per gallon. Is there enough evidence to support the advertiser claim using alpha of 0.05? All right, so for this one, I want to make a slight little change. So for this one, we're going to say population standard deviation. So we're going to say the population standard deviation of 5.5 miles per gallon. Because the way I wrote it, it was saying the sample standard deviation. But we're going to say this is the population standard deviation. So for this one, let's describe what are they trying to test. So what are they trying to test?
The mileage of a hybrid car.
Yeah. So the mean gas so they're trying to test the mean gas mileage because pretty much they're saying that the mean gas mileage is 50 miles per gallon. So we want to test that. All right, so let's go ahead and let's do our known alternate hypothesis. So if you kind of look at the problem, they're claiming, what are they claiming the mean mile per gallon should be of this hybrid car? Yeah, so they're claiming it should be 50. So we're going to say mu is equal to 50 mu. All right, so let's look at the alternate hypothesis. So for the alternate hypothesis, do they tell us that they think it should be greater than, less than, or should we put not equal to?
It would be greater than because we found it 47 and they said it's 50.
Well, they're claiming, or the manufacturer are advertising that the car should be 50 miles per gallon. But when we did a sample, we found that the sample was 47. So for this one, we're gonna put less than. Because we're gonna kind of go like, okay, we don't believe this advertiser, and we don't believe that 50 miles per gallon. So we're gonna say it's less than 50 miles per gallon, because we're not gonna say it's greater than 50 miles per gallon, because that's actually something good for them. Because if we could show that the mean mile per gallon for this hybrid car is more than 50 miles per gallon, that's actually something that's good for them because they can now advertise that it has more than 50 miles per gallon. If we kind of want to debunk their claim, we want to say that it's actually less than 50 miles per gallon. So for this one, you want to put mu is less than 50 miles per gallon. All right. Everybody go for my null hypothesis and alternate hypothesis? Okay. So let's go ahead and get some information. So let's get N. So if you look at N, they tell us they get 30 hybrid car. So N is 30. If you look at X bar, they say, if you look right here, it says, you find that in the sample, the average is 47 mile per Lagana. So they're saying from that sample, we found it to be 47 mile per Lagana. They put 47 here. Mu, we already stated is 50. And we have sigma where I tell you that this is a population standard deviation. So it should be 5.5. All right. Any question so far? All right. So let's go ahead and do part 4. So if you look at mu of x bar is just equal to 50. Sigma of x bar will equal to sigma, which is 5.5, divided by square root of 30. So let me calculate what that give me. There you go, 5.5 divided by square root of 30. 1.40. All right. Everybody good on sigma of x bar? So if I look at the difference, so let's look at the difference. Let's look at x bar and let's look at mu. How much of a difference do we have between x bar and mu?
Three.
Yeah, so if you look at the difference, we'll put this in red. It has a difference of 3. And if you look at the sample, well, if you look at sigma x bar, it's telling you you have a standard error or a standard deviation of x bar of 1.004. So if I have a difference of 3 and it's telling us that like normally we have a standard deviation of 1.004 for a sample size of 30, it's kind of telling us that we're gonna have a z-score over 2 standard deviations. So that's kind of telling us that this difference of 3 mile per Lagana is a significant difference. So let's actually find the z value. So we could do 47 minus 50 divided by 1.004. We got 3 divided. And you should get 2.99.
Should it be negative? Oh, there we go.
So you get negative 2.99. So that's kind of telling us it's significant. So up next, what we're gonna go ahead and do, we're gonna go ahead and get travel over to the TI-84. And what I wanna do, I just kind of wanna verify this, but also I wanna get the p-value. All right, but any question? I got the negative 2.99. All right, so let's go ahead and try. So let's go to the TI-84. Let's turn it on. Let's go to stats. Let's go to tests, and let's do the z-test. So first thing you want to do, change it from data to stats. So we're not given the data anymore, it's only stats. So we're going to do mean. Mean is equal to 50. Sigma was equal to 5.5. X bar was equal to 47. And N was equal to 30. And if you look at our alternate hypothesis, we put less than. So you want to put less than. All right. Any questions so far on any of my inputs? All right. So just remember your inputs should be looking like my inputs. If they're slightly different, it will give you a slightly different answer. So let me go ahead and calculate. So if you look at the Z value, pretty much their Z value and my Z value is identical, negative 2.98. We just rounded it up to negative 2.99. If you look at the P value, that's 0.001. So if you look at the type of tail that we have, this one will be considered a left tail test because we're saying less than. Right. Any question in regard to the output the Z-test gave me? Right, so let's go ahead and switch over. So this is what I enter when we were in the TI-84. I checked off that this is the left tail test, but I also said that the P value is equal to 0.001. So we'll say 0.001. Where you go with alpha? Alpha, if you look in this case, we said it was 5%, so 0.05. Give me a minute, my thing froze. Yeah, so our alpha was 0.05. So we'll put 0.05, we'll put P value, which is 0.001. So which one will be considered bigger, my alpha or my P value?
Alpha.
Which one?
The alpha?
Yeah, good. So alpha, so we check out the first one. So if you check out the first one, you want to say we reject the null hypothesis. All right, everybody good on why we select to reject the null hypothesis?
I have a question on how you got p-value.
Yeah, what's the question?
I just don't know how you got the 0.001.
Were you able to do the Z-test?
No.
Well, when you do the Z-test,
Oh, okay.
if you look right below the Z value, it says P, and that's the P value.
Okay, thank you.
Yeah, you're welcome. All right. Everybody good for part 6? All right, so let's do the last part. So the last part, you're gonna be the conclusion. So where you conclude. All right. So the conclusion, what we want to say there is enough evidence. So we say there is enough evidence to support the alternate hypothesis that the mean mile per gallon is less than 50, less than 50. All right, and that'll be it for that second problem.
I have a quick question. When we're doing step 5, is there, when we're looking at the right left tailed, are we getting anything from knowing it's right tailed or left tailed, really?
Well, you are getting something from the left tail and right tail because I kind of tell you which, like say if we're doing the normal CDF, it will tell you which tail you want to kind of focus on. So
Okay.
like, So like say for this one, we said with the left toe, correct? So if we go back to the TI-84, oops, let me turn it on. If we go to stance, if we go to test, if we go to zeta, if we were to draw this, we should expect that the left toe should be drawn. Well, for this one, the left toe isn't drawn because, well, here. Yeah, it's too small. Let me make this a little bit bigger. So let me make this 48. Let's draw it. So it will tell you like which side of the toe should be shaded. So that way you can always double check your answer if you do draw. It will tell you, hey, we shaded the left toe. Because say by chance you go and you select not equal to, and you do draw, you're gonna know something is wrong because you said it should be a left toe test, but for some reason it's shading the left toe and the right toe.
Got it. So that's more to compare our data with, you know, make sure we're on the right track.
Yeah, exactly. It is kind of to confirm that what you're thinking and what the calculator is giving you is correct. Because if you're thinking it should be a left toe and the calculator give you a right toe, then you know you entered something wrong into the calculator. So that would kind of give you a hint that you should go back to the calculator and just adjust it.
Perfect. Thank you.
No problem. So that's it for that last prompt. Any question in regard to that last prompt? So let's do one more, and then we're gonna move on to, we're still gonna be testing the mean, but we're gonna be testing the mean when we don't know the population standard deviation. So that's when we're gonna use the t distribution. But for this one, we're still using all right, so let's go ahead and do this one. So it says a manufacturer of sprinkler system designed for fire protection claims that the average activating temperature is at least 135 degrees Fahrenheit. To test this claim, you randomly select a sample of 32 system and find the mean activation temperature to be 133 degrees Fahrenheit. So just put a population standard deviation of 3.3 degrees Fahrenheit. At an alpha of 0.010, do we have enough evidence to reject the manufacturer claim? All right. So if you look at this one, we're testing the mean temperature all right. So what we're testing out here, we're testing on the mean activating temperature for the sprinkler, because pretty much we want to say if the sprinkler actually activate after 135 degrees Fahrenheit, because you kind of don't want it to activate when it is lower than that, because then that means like if it's like 120, 110, it's gonna get activated and pretty much everything gonna get wet. So we want to check to see if these are actually working. So let's do the null and the alternate hypothesis. So what do they tell us is the mean activating temperature?
133.
Well, that was from the sample that they got. Okay, if you look right there where it says we took 32 system and we found from the 32 system is 133 degrees Fahrenheit. So the 133, that's actually our sample mean. So what are they claiming is the activating temperature?
135.
Yeah, 135. Yes. So yeah, so the mean activating speed, not speed, but the mean activating temperature should be 135 or higher than that. So the null hypothesis is going to be that we trust the company and we're going to say it is 135 or higher than 135. So that's what this is saying. So that's saying that we trust the company or we trust the, what's called the sprinkler system, that it actually goes off after 135 or after 135 degrees Fahrenheit. But if you look at this one, we kind of want to reject the manufacturer claim. So we're kind of saying we don't believe the manufacturer. So if I don't believe the manufacturer, what should I say for the alternative hypothesis? Yeah, good. So we want to say it's less than, because we don't believe the manufacturer claim that is 135 or higher than 135. We're kind of suspicious about that, and we kind of think that it should be less than 135. So for the alternative hypothesis, we're going to put mu is less than 135. All right. Everybody good with that so far? All right. So let's do N. So for N, how many systems did they check out? Or how many systems did they sample?
32.
32, perfect. We already know the mean is 135. And we're saying the population standard deviation is 3.3. Everybody go with those notations so far? All right. So
I have a quick question.
Yeah.
What alpha is 0.10? That represents like our confidence level. What exactly does alpha represent when we're doing these?
alpha represents the chances of you making a type 1 error. So telling you the chances that we were to reject this null hypothesis and conclude the alternative hypothesis when the null hypothesis is actually true is going to be at 10%.
Okay, thank you.
All right. So right now what we're trying to do, we're trying to figure out, is this difference of 133 to 135, is that a significant difference? Because if you look at it right now, it's saying there's a 2 degrees Fahrenheit difference. So we kind of want to see if that difference could have been caused by random luck, or is this difference is actually a significant difference that we should kind of go ahead and then claim that their claim that is at least 135 is false. So let's go ahead and go to step 4. So for step 4, let's just enter some information. So we're saying 135. We're going to calculate the standard deviation of X bar for a sample of 32. So that'd be 3.3 divided by square root of 32. 0.583. Cool. So just remember the sigma of X bar telling you this is the standard deviation that we should expect for a sample of 32. This is not the standard deviation that we should expect for a sample of like 1. This is purely for 32. So it's saying if we randomly selected 32 sprinkler system, this is the standard deviation that we should expect for it. So let's go ahead and calculate the z-value, and then we're going to go ahead and double check it with our calculator. So for the z-value, we're going to say X bar, which is 133, minus the mean, which is 135, divided by 0.583. Let me go ahead and work that out. So 133 minus 135, that gives you a -2, divided by 0.583. 3, which gives you negative 3.43. All right, so we get a z-score negative 3.43. Like, before I even go on to find the p-value, you should kind of already know the p-value should be really, really small, because if you look at the z-value, it's pretty far away from the middle, and the middle is 0. So we should be expecting a really, really small p-value. All right. Any question before I go ahead and do the z-test? Okay, so let's go ahead and go to TI-84. So for the TI-84, we go on, we'll quit that. So you go to stats, you go to test, and you do a z-test. So for the mean of the population is 135. The standard deviation of the population was 3.3. X bar would be considered 133. N is equal to 32. And then you want to choose less than. So remember, less than, whenever you choose less than, that means this is the left tail test. So we go ahead and draw. Actually, let's do calculate for that. I could get a better accurate answer. All right, so if you look at the value that I got, if you look at the z value, we got negative 3.428, which is exactly what we got, negative 3.43. If you look at the p-value, you actually get 3.03. So right from the get-go, that should look kind of fishy for you. Like, you shouldn't put your answer 3.03, because that will be absolutely wrong. Because you do want to adjust it, because this is in scientific notation. So if you look at the e to the negative 4, that's telling me I get this decimal and move it 4 places to the left. So that means my p-value, well, your p-value should be 0.0003. And we said this is the left tail. All right. Everybody go on p-value and the z-value. All right. So let me go ahead and transfer back to my notes. So that's the new thing that I added to the notes. I checked out that this is a left tail test, and I also just put that the p-value is 0.0003. Everybody good with step number 5? All right, let's do step number 6. So for step number 6, we have p-value, which is 0.0003. We have alpha, which they tell us is 10%, 0.10. So if you look at which one's bigger, the bigger of the two will be alpha. So since alpha is bigger than p-value, we're going to conclude that we should reject the null hypothesis. So we rejected the null hypothesis. The null hypothesis was stating that the mean temperature that activates the sprinkler system is 135 or higher. So we're actually rejecting this. And what we're doing, we're concluding the alternate hypothesis. So we're going to say there is enough evidence to support the claim that
So when we're interpreting the results of the hypothesis test, it doesn't matter if we choose to word it as to support the claim or support the alternative hypothesis. It's interchangeable.
It's interchangeable because pretty much the claim is the alternative hypothesis. All right, but that's it for that last problem. Any question in regard to that last problem? All right, so let's move on down. All right, so for this next part, we're gonna be going over hypothesis testing when we don't have the population standard deviation. So this means instead of having the population standard deviation, we're gonna have the sample standard deviation. So kind of if you look at this formula over here, because the formula that we used for the last part was Z is equal to X bar minus mu divided by sigma divided by square root of n. So if you kind of look, the only thing difference is what do we use for standard deviation? So if you have the population standard deviation, you always want to use the population standard deviation because that's a more accurate reading. But if we don't have this population standard deviation, you have to get the next best option, which will be the sample standard deviation. So anytime we have the sample standard deviation, you do want to use the t-distribution. And for this one in the calculator, this is just called the t-test. Right. So just remember, in order to use the z-distribution, you need population standard deviation. In order to use the t-test, you're going to need a sample standard deviation. So if the only thing given to you is the sample standard deviation, you use the t-test. If you're given the sample standard deviation and the population standard deviation, you always go with the population standard deviation. So that's when you go for the z-test. So this is z-test. All right. Any question in regard to when to use the t-test versus the z-test? All right. So let's go ahead and let's run a problem.
On the notes, the formula states that n has to be greater than 30. So is that also included like the CLT theorem or test, CLT test?
Yeah, that's just for the CLT test. So you're saying like if we don't know the data set is normally distributed, then you want to know that the sample size is greater than or equal to 30.
So if it's not greater than 30, then we can't use this, right?
Yeah. So if it's not greater than 30 and the problem doesn't specify that it's a normal distribution or approximately normal distribution, you can't use the CLT. Well, you can't find this value. All right, so let's do this first problem. So for this one, it says a manufacturer of rubber chemical by a batch process had a normal yield of 690 pounds per batch. A new process is tried experimentally on 12 batches with the following yield. So, is the yield of the new process a significant difference from that of the old process? At the alpha of 0.05 level significant, is there evidence to conclude that the yield of the new process is significant? So let's just say is significantly different from the old process. Assume the data is coming from the population that is normally distributed. So if you look at this, we have a sample size of 12. So if it has a sample size of 12, if you check the central limit theorem, it won't pass the central limit theorem. But the good thing about this one, they told us that we should assume the data is coming from a population that's normally distributed. So since they're telling us that we already know the data set is normally distributed, you could just go ahead and just assume that so we don't have to check the central limit theorem. Because we already know, because they're already telling us it's normally distributed. All right. So the first thing that you wanted to do is, in a sense, to describe the parameter that is being tested. So the parameter that's being tested in this case is, oops, don't want to do a highlight, the mean yield of, yeah. All right, so what we want to do, we want to test the mean yield of the new batch process. So we want to see if the mean yield of the new batch process is different from the old one. So that's what we're testing. So what do they tell us is the mean yield of this process normally?
690.
Yeah, 690. So we'll put mu is equal to 690. So for this one, are you telling us that we think it should be greater than 690, less than 690, or do we just want to prove that it's different from 690?
Just different.
Yeah, just different. So the alternate hypothesis will be, it's just different. All right. Everybody good with step number 2? All right. So step number 3, we're gonna put n. N, if you look at it, they tell you they did 12 batches, so that means n is 12. So if you look at it, they don't give me the sample mean, but they do give me data. So I'm gonna actually use that data to be able to get the sample mean a little bit later on. But for right now, just know that we're gonna get the sample mean, and also if you look at it, they don't give me a population standard deviation, they just give us the data. So we're gonna use the sample standard deviation from that data. So they do give us mu, which is 690. All right. So far we have 12, which is n. We have 690, which is mu. We have x bar and s, which is unknown to us because we still haven't punched it into our calculator. Also, we do want to put degree of freedom. So for this one, what will be my degree of freedom? Yeah, good. 11. In case you forgot, the formula for degree of freedom is n minus 1. So 12 minus 1 is 11. All right. Everybody good so far with that information? All right. So right now we're gonna go ahead and we're gonna actually jump into the TI-84. So let's go to the TI-84. So for the TI-84, we're gonna go to stats. We're gonna go to edit, and we're gonna edit L1. So I'm gonna go ahead and enter the 12 data set that it has. So the first one was 620. The second one was 590. Third one was 660, and so on and so forth. All right, so I enter all 12 of my data set. So now I'm gonna go here where it says stats. We're gonna move over here to test. Remember, we're not given the population standard deviation, so we're not doing a z-test. We're actually gonna go ahead and move over to a t-test. And the one thing I do kind of want you to note for the t-test, if you look right here where it says fx, it's asking you for the sample standard deviation. So that's how you could kind of also just kind of back up what you already know about the t-test, that it only wants the sample standard deviation. Because if you do a z-test, it's going to ask for the sigma. So you kind of know for a t-test, it's always going to ask for s. So if you're in the t-test and you know sigma, you're in the wrong test. Like you want to be on the z-test. So first thing I want to go ahead and do, I want to tell the calculator, hey, look at the data set. So go data. And the only thing you have to enter here is our mean of the population. So the mean of the population was 690. If you look at the list, you tell it L1. If you look at the frequency, leave it as 1. And for the alternative hypothesis, and we said not equal to, we put not equal to, and let's go ahead and calculate this. So if you look at the sample mean was 672.5. So I want to fill that out. So 672.5. If you look at S of X, its standard deviation was 43.72. So that's kind of telling us we have a high standard deviation, because if you look at it, it's 43.7. So if you look at the t-test or the t-value, we get negative 1.39. So negative 1.39. And lastly, if you look right here where it says p, that's my p-value. And this is a two-tailed test of 0.193. All right. Any questions so far on the t-value, the p-value, the sample mean, or my sample standard deviation? All right. So I'm gonna go ahead and switch over back to the notes. For that way you can kind of see what did I already enter for the notes. So pretty much whatever I highlight in yellow, this is what I enter for the notes. So if you kind of want to follow along and enter that also, you could do so. All right. Everybody good with that? All right. So let's go ahead and say compare our p-value to our alpha. So if you look at our alpha was given to us as 0.05. So we'll say 0.05. If you look at our p-value, it was at 0.193. So in this case scenario, which of the two will be bigger, my p-value or my alpha? Yeah, p, perfect. So since p-value is bigger than my alpha, that means the difference that we have is not a significant difference. So you want to go to fail to reject. So before we kind of make the conclusion, let's kind of like go over that. So when we fail to reject, we're saying that D2 value, there's not a significant difference compared to our standard deviation. Because if you look at 162.5 and if you look at 690, there's approximately a difference of like 17. But if you look at the standard deviation, it's 43.72. So that's why we're getting that it's not a significant difference, because saying like, yes, there is a difference of 18, but since the standard deviation, or in this case, the sample standard deviation is such a high sample standard deviation, it's kind of telling us like you should expect variation. So that's why this difference of 17 is not that significant. So we'll say there is no mean yield. All right, so that'll be the answer that we put. We'll put there's not enough evidence to conclude that the mean yield of the new batch process is different from 690 pounds. Any question for that last problem? All right, let's do this next problem. Oops, went too high. So for this one, we have a tire manufacturing plant processed 15.2 tire per hour. New machines are recommended, but will be expensive to install. Before deciding to implement the change, 12 new machines are tested. They produce a mean of 16.8 tire per hour and a sample standard deviation of 1.58. Is it worth buying the new machine? Assume the data come from a population that is approximately 1. So once again, if you look at this one, we do have a small sample size. So we have a sample size of 12. But for this one, that's okay because they tell us we could assume the data set is normal. So we don't have to use a central limit theorem or anything like that because they already told us that from the population that we're sampling, that population is actually normal.
Are we going to get to a point where we use a central limit theorem on these type of questions?
For these, I'm trying to remember, like for problem on the homework, there should be some that you're going to need a central limit theorem. But I don't think I wrote any of them here, but for the homework, I'm pretty sure there should be some. All right. So for this one, what we want to do first, in a sense, to describe the parameter that is being tested. So what are we testing?
The amount of tires being produced per hour?
Yeah, the amount of tire being produced per hour, but for this one, the key thing is that the mean tire being produced per hour. So, oops, not a highlight. The mean tire. So we're saying the mean tire being produced per hour. Yeah. All right, so for this one, if you read the problem, you kind of want to see if their process or their machine is on par with the new machine. Because if it's not on par, they're going to buy this new machine. But if the new machine and the old machine are kind of spitting out the same amount of tire, there's no need for them to buy the new machine if the old machine is actually working just fine. So how much tire did the old machine give you per hour?
It would be that 15.2 per hour?
Yeah, 15.
Or,
So we'll say mu is equal to 15.2. Because that's what they are producing right now. So they're producing 15.2 tire per the hour. So you put mu again, you put 15.2. So for this one, what are they trying? Yeah, it's all fine. Like we all mess up sometimes. For this one, when would they replace this old machine processing or manufacturing plant? will it replace it if the new machine is giving me less than 15.2, more than 15.2, or different from 15.2? Yeah, well,
More.
you can replace it when it's more than 15.2. Because if the new machine processing system give me actually less than 15.2, then you really don't want it, because why would you want something that's producing less than what you already get? So we only want to see if it produced more than 15.2. All right, so let's go ahead and do n, x bar, mu, and s. So if you look at n I already said was 12. If you look at x bar is equal to blah, 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 16.8. And if you look at this part, it says the sample standard deviation of 1.58. So they're not telling me this is the population standard deviation. They're telling me this is the sample standard deviation. So that's why S is 1.58 and mu is 15.2. All right. Everybody good so far on step 3? All right. And lastly, degree of freedom. Degree of freedom is 11. So right now what we want to do, we want to show that this is a significant difference from this. Because if you look at it, it's pretty much saying there's a difference of 1.6 higher. So we want to see if that difference is a significant difference for us to warrant buying this new machine. Because also think about it, that's per the hour. So if they're working 10 hours, that means it produces 16 more tire for those 10 hours. So it might be worth buying, but also it might not be worth buying depending on what the price is. So that's what we're gonna be computing right now. So what we're gonna go ahead and do, we're gonna jump straight into the calculator and get into this problem. So we're gonna go to class calc, TI-84. So for the TI-84, we go to stats, we go to tests, we do a t-test. And remember, for this one, the reason we're doing a t-test because we have sample standard deviation. If you would have population standard deviation, you do a z-test. But since you have a sample standard deviation, we're going to use a t-test. All right. So if you look at mu will be 15.2. 15.2. If you look at x bar will be 16.8. If you look at S is equal to 1.58. N is equal to 12. For this one, my alternate hypothesis should be greater than. And let's go ahead and calculate this. Well, before I hit calculate, any question on anything that I inputted for the t-test? All right. So if you look at the t-value, we get 3.507. I'm going to round that off to 2 decimal places. I'm going to get 3.51. So, oops. We'll do this in blue. 3.51. If you look at the p-value, we get 0.002. So this is 0.002. Also, if you look at it, since we say greater than, that means this is the right tail test. So right tail test. All right. Everybody good? I got the t value to be 3.51 and the p value is 0.002. Okay, so I'm gonna go ahead and transition back to my notes. All right, so if you look at my notes, I put t value is 3.51. I put that the p value is 0.002, but I also put that this is a right tail test. Any question in regard to that? Okay, so let's go ahead and get our alpha. So if you look at this problem, alpha isn't actually given to us. So since alpha isn't given to us, what should we assume alpha to be? There's a value I tell you that it should be assumed to be. Yeah, 0.05, thank you. So we'll put 0.05 over here. So if you look at the p-value, and if you look at the alpha, alpha is 0.05, p-value 0.002. So that means alpha is actually bigger than p-value. So that means we select this first one over here. Since p-value is less than or equal to alpha, that means we should reject the null hypothesis. Any question on why we reject HO? All right, so since we reject HO, that means there's enough evidence to support the alternative hypothesis. So the alternative hypothesis is saying that the new machine does process more tire. So we'll say there is enough evidence to support the claim that all right, so we put there is enough evidence to support the claim that the new machine had a mean output tire per the hour greater than 15.2. And that will be it for the last one. Any question for the conclusion?
I have a quick question. This in the last problem was asking for the degrees of freedom, but we weren't using the t-table at all. Why was it asking for the degrees of freedom?
It asked for the degrees of freedom if we were doing the classical method. But since we're skipping the classical method, there's no need for the degrees of freedom.
Got it.
Well, let's see. Yeah, there's no need for the degrees of freedom. It's only if we're using the classical method.
I was getting the t-table already.
Yeah, sorry about that. All right, but that's it for the last conclusion. Any question in regard to the last conclusion? Or that last problem? All right. So let's go ahead and move on to this one. All right, so we're gonna go over to distinguish between a statistical significant and practical significant. So when we talk about statistical significant, is you go through the process of finding the test statistic, finding the p-value, and at the end you reject the null hypothesis. So that's what we mean with statistical significance. So if I go through the entire process, we go through the entire process and we find that the alternative hypothesis is correct by rejecting the null hypothesis. So that's statistical significance. Practical significance is looking at the difference of the two and going like, will anybody care if this was actually a difference? So if we say the difference was from like 5.1 to 5.2, yes, we were able to prove that it's statistical significant, but we kind of wanted to be practical significant where that 0.1 of an increase actually does matter. Because if that 0.1 of an increase doesn't really have any practical significance, then why even report it? So right now we're gonna do a problem where we are gonna get that it's statistical significant, but we want to test to see if it has practical significance. All right. So let's go ahead and do this next problem. So for this one, it says in 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine if the average has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean age of 25.2 with a standard deviation of 4.8. Determine whether the mean age had increased using a significant level of alpha equal to 0.05. So if you look at this problem, they don't tell us the distribution is a normal distribution, but if you look at the sample size take care of that because we have 1,200 as a sample size, which 1,200 is clearly bigger than 30. So we could say this is approximately normal. And the reason it's approximately normal is because of the central limit theorem. CLT. Everybody good with that so far? Okay. So let's do the first part. It says, in a sentence, describe the parameter that is being tested. So mean age of mother at the time of her first childbirth. So that's a parameter that we're trying to figure out. We're trying to figure out the mean age of mother at the time of her first childbirth. So let's go ahead and do the null hypothesis. And the alternate hypothesis. All right. So what was the last known mean age of a mother at the first time they had a child?
25.2.
Perfect. There you go. 25.2. 25.2. So what are they trying to prove? Are they trying to prove that less than 25.2 is greater than 25.2 or different from 25.2?
Greater than.
Yeah, greater than. Because the keyword here is increase. Where does it say increase? There we go. It said increase right there. So you want to put greater than. All right. Everybody go with that so far? All right, so let's look at the N. N in this case is 1,200. If you look at from that 1,200, they were able to find the sample mean because like just look at it and you see how all of this is in the same sentence. So since all of that is in the same sentence, you pretty much know the 25.5 and the 4.8, both of those are coming from that sample. So we're gonna say X bar is 25.5. We're gonna say mu is 25.2. And we're gonna go sigma is 4.8. Or sorry, it should be S. S should be 4.8. Any question in regard to that so far? It should be 2. All right. So for this one, since we're given a sample standard deviation and pretty much that's it. Since we're given a sample standard deviation, we're going to go ahead and use the t-test. So let's go ahead and use the t-test. So let me transition over to TI-84. So TI-84, we're gonna go to stats, we're gonna go to tests, and we're gonna go to a t-test. So for the mean, we're gonna put 25.2, so 25.2. X bar is gonna be 25.5. Standard deviation of the sample is 4.8. N is 1200. And then our alternate hypothesis should be greater than. Any questions so far for the input on my t-test? All right. So let's go ahead and calculate this. So if you look at my t-value, we get 2.17. If you look at the p-value, we get it to be 0.015. So 0.015. Sorry. So you should get t-value 2.17, and you should get p-value of 0.015. Any question on how I got the t-value or the p-value? All right, so let me go back to all right. So that's what I put for t. I put t is equal to 2.17. I put p-value is 0.015. So p-value 0.015, alpha, in this case, I forgot what I said, alpha was equal to 0.05. So which one's bigger, p-value or alpha?
Alpha.
There you go. So since alpha is bigger, you reject the null hypothesis, and for this one you say there is, oops. Oof. So for this one, we'll put there is significant evidence to support the claim and whatever the claim was. So this is when we have statistical significance. Statistical significance, we go through the whole process, and at the end, we reject the null hypothesis based off of the p-value or based off of the t-value. But the thing is, if we actually go back and look at it, so if I go ahead and look at this, so you go like, will anybody really care if I tell you that the mean age when a mother first gives birth to their first child has gone from 25.2 to 25.5? Do you think that that will be a practical significance where people will actually care about that age? No, not really. Like if I would have said it went from 25.2 to 28, then will be more practical to us because that's a kind of a big jump. But if I tell you it just jumped from 25.2 to 25.5, like that's not that much of a big of a gap that it will make practical significance to us. Also, if you kind of look at our data set, we had a big sample size, and usually when you have a big sample size, it's gonna kind of give you misleading information. Because say if I go back and we do a t-test and it changed the sample size from 1200, say, let's do 30. Now you get something that's not significant. So like the only reason or the true reason why you got that there's such statistical significance is because we have such a big sample size. So since we have such a big sample size, it's saying any little difference we might have, it could conclude that it's a big difference because we have such a big sample size. So that's why you kind of want to be worried, like, yes, we did statistically prove that there's a difference, but you also kind of want to think about like practical term, is it a practical difference where it does make a huge difference in the long run? All right, but that's it for that last problem. Any question for that last problem?
So for practical significance, will we be, like, how would we test practical significance? Because wouldn't that be more matter of opinion though sometimes?
Yeah, cause you do. That's when they want to like bring in like an expert, somebody, and see like based off of their expert opinion, like is that a big enough difference? Like say like going back to the one about the tire place, like you kind of want to go like, okay, is it a big, is it a practical significance where if we could produce one more tire an hour, does that warrant me buying that new machine? So you kind of have to look at the long run, and you kind of want to have like an expert in that field because you don't want to go by your expertise if that's not your expertise. You kind of want to go with somebody that knows. So like say for the tire, if that one tire per hour is going to make a huge difference, then you want to actually go ahead and buy it. But if they're kind of looking at that one tire, it's not going to make that much of a practical difference, then they shouldn't warrant buying that new machine. Like yes, the new machine is better, but
Okay, so it would be like a piece of data for like cost analysis of like when the machine would pay itself off based on the new production.
yeah, exactly. And you kind of also want to go the lifeline of the machine because depending on how long the machine gonna last, like you go like, is it gonna last long enough for that machine to actually pay it off? Because if you're saying the machine gonna pay it off in 10 years, but the machine usually break down after 8 years, then you go like, it doesn't make sense to buy this new machine because it's never gonna pay itself off.
Gotcha. So so practical analysis, the practical significance is just a separate part for more thorough analysis.
Yeah, it's more thorough analysis. Like we're not like for the tests or for quizzes, I'm not gonna give you anything like that. Where I'm gonna tell you like, okay, do the practical analysis of this. That is kind of like further on in statistics. But for us, where you're gonna focus on statistical analysis or statistical significance.
Is there a calculation for practical significance or a formula?
Well, there's not like a formula, but kind of going back to that the tire place, like
Okay.
where you go like, okay, how much does it cost? How long did it take to pay it off?
Gotcha.
And
Okay.
when is it going to start making a profit for us? So they're not like a formula for all cases. It kind of depends on the scenario. All right. So let's transition back to the notes. Here, you give me a minute. I'm just looking up something real quick. All right. Let's stop share. All right, guys. So that's actually going to be it for today. So today, pretty much we're going to stop at 10.3. There you go. So on Monday, we're going to get started with 10.4, and pretty much 10.4 will be the final section that we're going to go over, and then we're pretty much going to focus on the final. So for the quiz on Monday is going to either cover hypothesis testing for the mean when sample standard deviation is given, or it's going to be hypothesis testing for the mean when the population standard deviation is given. So it's gonna be one of those two, and you're gonna just have to do a hypothesis test for that data set. Any question in regard to Monday quiz?
Do you know which one it's going to be, or we just kind of have to study both?
Well, I already know which one's gonna be, but I want you to study both.
Okay, cool.
It'll be one of the two. Cool. And for the quiz is gonna have one singular question. It's gonna be do a hypothesis test. So hopefully everybody kind of grasps the idea of doing a hypothesis test, and it should be that bad.
So the quiz is going to be on 10.2 and 10.3? Or just figuring out which one to use?
10.2 is proportion, if I remember correctly. Yeah, the test is only going to be on 10.3 because 10.2 is when we're testing hypothesis for the proportion.
And when you say one question, that's not like an all or nothing. It's going to be broken down kind of like into the 7 parts that we did. Or
It's actually going to be broken down into the 4 parts. So I'm going to show you the 4 parts that I'm going to break it down to.
so it's not like if we get it wrong, we're getting 0 out of 25. We might get some of the parts.
Yeah.
I mean, hopefully if we're getting
Isn't Monday Memorial Day?
Is it Memorial Day?
we shouldn't have class on Monday, I don't think. That's up to you.
Oh yeah, it's Memorial Day. Well,
Definitely tomorrow.
you'll just have a quiz and then that's it. So we won't have lecture, but we'll have the final lecture on Wednesday, and then like it shouldn't take that long. It should take 30 minutes, and then we'll start reviewing for the final.
So we're going to still have a quiz on Monday then?
Yeah, let's still have a quiz because that way you can have more quiz to drop. Yeah, so the quiz on Monday will be broken down like this. So the first part, it will be state the known alternate hypothesis. The second part will be get your test statistic. Test statistic is either going to be the z-value or the t-value. You're also going to have the p-value. So the p-value, you have to just state whatever the p-value is. So say 0.01. Interpretation, that's going to be you just saying reject HO or fail to reject HO, and then you choose a conclusion. So that's how the quiz is going to be broken down on Monday. You're going to have to do state the known alternate hypothesis, find the test statistic, and find the p-value, interpret it by just saying either to reject the null hypothesis or fail to reject the null hypothesis, and to state a conclusion. Any question in regard to the quiz? Or any more question in regard to the quiz? All right, so if there's no further question about anything, what I'm gonna do, I'm gonna close down the meeting. And if you do have any question, I'm gonna have office hours right now. So you can just jump in and just go to my office hour, and you can just ask any question that you might have on quiz, on lecture, notes, whatever you have. All right, bye, I'll see you Wednesday. Have a good weekend.